So if you missed today's class, we did things a little bit differently. We had two different stations that we switched through halfway through the class. The first station, you were working on Alex's homework. And the second station, we had a very small group discussion that eventually led to these notes. We took quick notes on polynomial types and quick notes on multiplicity. But the main part of it was kind of an exploration on Desmos. So we're going to start off just exploring some ideas with Desmos. And then formalize that into some notes. So the first thing I asked our students to do was to take a look at this equation here and take a look at the graph and start to just kind of notice everything about the graph. So we can probably notice that, all right, there's a y-intercept at -2. There's zeros at 1 and -2. Okay. It has a positive even end behavior. Both are pointing up. What else do we have? Yeah, then I guess if we look at the equation, some other things we can notice. It's a second degree polynomial. It's in standard form. So one challenge that I asked our students to do then with this information was to, hey, can we write this in factored form? And if we use those zeros to write it in factored form, that -2 and 1, okay, we can probably make a guess that our factored form would be something like f of x equals x plus 2 times x minus 1. Remember how those signs flip between our factors and our zeros. So let's plug that in and see if we're right. If I go f of x equals x plus 2 times x minus 1, I type in that equation that you guys just estimated. We can turn that on and off and see that, yeah, we nailed it. This is exactly right. So that's one cool thing we can do just from reading our graphs is we can go from standard form to factored form, or at least pretty close, because there are multiple ways we can hit these zeros and still have a different function. So check this out. I'm going to throw a 2 in front of my factored form. And if I do that, you'll notice that the graph started kind of stretching downwards now, as opposed to, notice how it's stretched downwards from the red graph, as opposed to hitting it perfectly. We still have the zeros where we want them, but now the graph has kind of been modified a little bit. We can go that other direction as well if we use a number less than 1. Go maybe 0.25 and make it go wider and stretch up. But just kind of notice how that changes some things. Another thing we can do is we can just throw a negative out in front of this and notice how that flips our end behavior around. Now we have a negative end behavior, but we're still hitting those same zeros. Okay, and the reason that works is if we were to multiply this whole thing out, we would get this negative distributing in to both of our polynomials, and that would end up with a negative leading term. So let's clear some of this stuff out. Let's look at another polynomial here. Group another one that's x to the third plus 2x squared plus 5x minus 6. Oh, sorry, I had that typed in correctly. Minus 5x minus 6. So I'm going to zoom out just a little bit so we can see this a little more clearly. It looks like here, if we start making some observations, we have a third degree positive polynomial. We know that from our graph here. So it should have that positive odd end behavior, which it looks like it does. Okay. We should have 3 solutions or 3 zeros, which it looks like we do as well at -3, -1, and 2. And what else do we notice? X or y-intercept at -6, it looks like. Okay, so Now I kind of want us to make a prediction. What would the factored form look like for this? We know we have zeros at -3, -1, and 2. So our factored form should be f of x equals x plus 3, x plus 1, times, and I'm running out of space here, sorry, x minus 2. Let's test that out. X equals x plus 3, plus 1, minus 2. Cool. Looks like we're good there. Then if I were to ask you to kind of, hey, if we wanted to stretch this at all or maybe squish it down a little bit, we can throw some leading coefficients out in there, maybe like 0.5 to make it kind of stretch smaller, maybe 2 if we wanted to stretch higher. And if we wanted to flip that completely, we would hit negative. And you can see how that graph shape has changed. We now have that negative end behavior for our third degree polynomial. All right, last thing I want to kind of show you is if we were to kind of take this black graph and let's say we wanted to shift this 1 over to 0. This factor here, x plus 1, let's say we changed to x plus 0. Okay, nice. So we did what we kind of wanted to do, right? I'll turn off this red graph. We shifted that 0 over to 0. But some of you guys explored this in an earlier problem where if I have x plus 0, that's just the same thing as having x, right? So our formula would then be x plus 3 times x minus 2. Normally, we're going to see that written with the x out in front. So if I rewrite my equation just slightly, I'm going to get rid of this x plus 0. I'm going to throw that x out in front. So that same graph, right? 0 at -3, 0 at 2. But we also have this 0 at 0 now. So even though it kind of looks tricky, this x, when it's out in front, still is a factor. It may not be in the parentheses like the rest of our factors are, but it's still a factor. It results in that third solution to our polynomial. So let's take a quick pivot here and jump into our notes. So your notes, real quick, polynomial types. We're just going to fill out this table real fast. No need to do any example problems. We're just making the connection between standard form, factored form, and behavior. And also want to start applying some names to these. You don't have to memorize these, but I do want you to have exposures to them. So if we have a second degree polynomial, it's going to have 2 factors. And that we call that a quadratic. And you guys should already know this end behavior. We have a positive end behavior that goes up and up, and a negative end behavior that goes down and down. Okay, third degree polynomial, 3 factors. We call that a cubic. End behavior could start low and high, or when it's negative, it could start high and low. Fourth degree, we're back to even, so it should match that quadratic shape. We have 4 factors. It's called a quartic. Up and up, down and down are possible behaviors. And the 5th degree polynomial has 5 factors. It's called a quintic. And it's going to have that odd shape, just like our 3rd degree did. And I noticed that I made a typo there. Quintic is now spelled correctly. Sorry about that. Okay, let's go back to our Desmos graph real quick. And let's explore one other concept today called multiplicity. So I'm going to throw 2 graphs up here. 4 2 times x plus 1. Turn that on so we can see it. And I'm going to throw on 3 x plus 3 times x plus 1. Let me change the color of one of these so we can do a comparison. So we got a red graph and a blue graph. And I want you to kind of look at these and start making a few different comparisons first before we talk about anything. What do you see that's the same? What do you see that's different? So Both of these have three factors, right? We have x plus 4, x plus 2, x plus 1, and we have x plus 3, x plus 3, x plus 1. So we should have three solutions for each, which means we should have three zeros for each. For a red equation, that makes sense, right? We got a 0 at -4, a 0 at -2, and a 0 at 1. So that one's all good. But let me kind of hide the red one real quick and look at the blue equation. We have a 0 at -3, and we have a 0 at -1. And what's interesting is at -3, instead of the graph passing through and coming back, the graph just sort of kicks back at that x-axis, right? Now, check out that equation. So at -3 here, our factor should be x plus 3 is our factor. And if we look at that in our equation, notice how that shows up twice. That's what having a multiplicity is called. So that's something that you'll jot down the definition before, but when a factor shows up more than once, it's said to have a multiplicity. In this case, it has a multiplicity of 2 because it shows up twice. So if I turn my red graph back on, you'll notice, hey, we don't have any multiplicities in the red graph. X plus 4, x plus 2, x plus 1, they all only show up once. And at each of those spots, we pass through our x-axis. But with our blue graph, we have x plus 3 has a multiplicity of 2. So this is going to kind of kick back. And the x plus 1 just shows up once, so that's one of our pass-through points. Now, let me turn off the red graph here just to show one final point. Let's say we took our blue graph and we said, okay, instead of x plus 1, let's say we had a multiplicity of 3 and we went x plus 3, x plus 3, x plus 3. Notice now how our graph still goes through that 0 there. So we do intersect. We don't actually kick back, even though this has a multiplicity. When we have odd multiplicities, we are going to pass through. When we have even multiplicities, we are going to kick back. So let's quickly kind of formalize this learning in notes, and then we'll be done for the day here. So jump back to our slides. And this will be on the back side of your note sheet, multiplicity. Get a quick definition down. So multiplicity is how often a certain root or 0 is part of the factoring. So just kind of like we talked about, odd multiplicities cross the x-axis. That's what this red graph looks like. This red graph is an odd multiplicity. In all three cases, right? There's three instances, 1, 2, 3. And actually it shows up as odd in our blue graph as well, right over here, but then we have an even multiplicity at this point where the graph kicks back. And they're just going to just touch the x-axis. So I want to show you just a couple examples of how these might be written out. So if we have, let's say f of x equals x plus 1 times x minus 3 times x minus 3. Let me make sure that's an x there. We can write it like that, right? And we have, this has a multiplicity of 2. And I'll just put mult of 2, so I don't have to write that out. Okay, and another way we can write that, or is a little more shorthand. We can go x plus 1 times x minus 3 to the second power. Okay, notice how we, instead of writing x minus 3 twice out there, we wrote it as x minus 3 with an exponent. We're taking that whole thing, x minus 3, and we're timesing it twice. Okay. Let's see why that might come in handy. In this next example here, if we had f of x equals, let's go x plus 4 times x plus 4 times x plus 4 and x minus 1 times x minus 1, right? That's a lot of things to write out. Okay, so we have this x plus 4 has a multiplicity of 3. This x minus 1 has a multiplicity of 2. And we can actually write this out a lot cleaner if we just go, say, or f of x equals x plus 4. And since it has a multiplicity of 3, we can take it to the third power. And x minus 1, since it has a multiplicity of 2, we can take it to the second power. So those are the notes for the day. Thanks for paying attention to that discussion. And we do have an exit ticket that you'll need to make up. No practice, though, other than getting your Alex homework done.